This video is about why nonlinear activation functions are so crucial to neural networks. Some examples of nonlinear activation functions are the sigmoid, tan, h, and ReLU functions, which I show here. For instance, the sigmoid function takes in negative values of x and outputs a value close to 0, or it takes positive values of x and outputs a value close to 1. This sort of functionality turns out to be a really important operation for neural networks. I'll just show you here where in a neural network activation functions are used. Here's a simple neural network with two inputs, x1 and x2, and two weighted lines to a single node. At the node, the two inputs, x1 and x2, are multiplied by w1 and w2 respectively, and the terms are added up. And a bias term, which is just a single floating point number, is also added to that total. This is the way neural networks worked when they were first invented, when people didn't realize how important activation functions are to neural networks. And so in present day neural networks, nonlinear activation functions are applied at the node after the summation has happened. So you can represent the nodes here as, see, the summation happens, and then the ReLU, for instance, function is applied after that. So a neural network with activation functions can solve a lot more problems than a neural network that doesn't use activations. For example, a neural network with activation functions can solve the XOR problem, but a neural network without them can't. So let's look at the XOR logic function here that takes two arguments, x1 and x2. When x1 is 1 and x2 is 0, so for instance here, the function outputs a 1, or if x2 is 1 and x1 is 0, then the function outputs a 1. In other words, only one of the inputs can equal 1 if the output is to equal 1. So if x1 and x2 are both 0, or if they're both 1, then an output of 0 results. So it turns out that a neural network without activation functions can't correctly output this table. Put another way, if we were to plot those 4 points on a graph here, a neural network classifier without activation functions can't draw a line that separates the purple points from the orange points, because the neural network without activation functions can only draw a straight line, and no straight line can separate the purple points from the orange points. At best, you can only get 75% accuracy when trying to draw a line that separates the purple points from the orange points. So in this case, you get 75% accuracy. Anything on the left of the red line gets an output of 0, and anything to the right of it gets an output of 1. So in this case, it gets this guy wrong. So it gets 75% accuracy in this case. But, we can't have 75% accuracy when representing a fundamental logical operation like XOR. Let's look at a neural network that doesn't have activation functions, which tries to solve the XOR problem. This neural network has just one hidden layer, let's say, and the first node is called H1. And it has two weights, W1 and W2, which are multiplied with the inputs x1 and x2, and their weighted sum is computed. Similarly, the second node, which is called H2, has two different weights, W3 and W4, that are multiplied with the inputs x1 and x2, and the weighted sum is computed. Y has two weights, W5 and W6, which multiply with the outputs of H1 and H2, and don't forget the bias terms. I forgot the bias terms there. You can use algebra to prove that when you're trying to find a single formula that outputs the results for the XOR table, it can't be done. In each of the 4 panels that you see here, I show x1 and x2 equaling different values and what the XOR output should be in those cases. So for instance, in the top left panel, x1 and x2 both equal 0 here, and so in this case, an output of 0 should occur. I then derive what the h1, h2, and y equations should be in this case. And I do the same thing for the other cases. I won't talk about the details of the proof, but the details are provided here, and you can pause the video at different spots to see how I show this. But it turns out that when you combine the equations and try to find the values of the weights that will solve the problem, you end up with the equation 1 plus 1 equals 0, which means there isn't a solution. There is no linear equation which can output the XOR results. The argument I make here, however, doesn't prove that only a neural network with activation functions can solve the XOR problem. For instance, maybe we could add more nodes to the hidden layer in the middle and solve the problem and enable the neural network to properly represent the XOR logic function. Turns out that if you do this, if you add extra nodes to a layer, this doesn't actually help. But let's take a look at why. So let's add a node called H3 to the network. And this H3 node has its own set of weights, W7 and W8. And there's the formula for H3 there. The equation for Y will have to change in order to accommodate this new node. And we can expand on the work that we did earlier and extend the algebra to prove that adding this extra node to the middle layer of the neural network doesn't help things. When you work out the details, you still end up with an equation that says that 2 equals 0. And you'll continue to get an impossible equation regardless of how many nodes you add to the network. So adding more nodes to the network doesn't help. The neural network still can't solve the XOR problem, so let's try something different. What if we add more layers to the neural network? Turns out this too doesn't help, but let's take a look at why. The computations of the network can be represented by matrix multiplication, as you see here. So H1 equals Wx plus B. Let's add another layer called H2 and see what happens. The layer H2 takes the H1 result and applies a matrix multiplication of the H1 output with the H2 weight matrix, which I've called W2 and which appears in purple here. When you work out what this means, you see that the W2 matrix times the W matrix can just be expressed as a new matrix, which I call W new here. And this part of the equation, W2 times H1's bias term, which is called B, plus H2's B2 bias term, can be simplified to just a new bias term I call B new. In other words, the two-layer neural network can be collapsed to a single-layer neural network, H2 equals W new X plus B new. What this means is that adding another layer hasn't added any needed complexity to the neural network. The new neural network is still just computing Y as a linear function of the inputs x1 and x2. The neural network still boils down to being a linear equation, and as we saw earlier, a linear equation can't correctly output the XOR table. It can't correctly represent the XOR function. So what we've seen so far is that without activation functions, adding new nodes to a layer of the neural network can't solve the XOR problem, nor does adding new layers to the neural network help. In the next part of the video, let's see how far we can go to solving the XOR problem without activation functions. We'll see just how close we can get to representing the XOR function using just linear equations, and then we'll see where activation functions have to step in to finally solve the problem. So we're still looking at a single layer neural network that has inputs x1 and x2, and two nodes h1 and h2 in the hidden layer, and an output node called y. Let's say the linear equations for h1 and h2 look like this. I picked these two h1 and h2 linear equations by hand because they give us sort of useful intermediate results that get us really close to solving the XOR problem. Here's a table of the four different values x1 and x2 can have, and their corresponding H1 and H2 outputs when the equations for H1 and H2 are as they appear up above. And in green, we see the desired output, the output that the XOR function outputs. With the H1 and H2 linear equations I've written up above, we see that either H1 or H2 is a negative number when we want an output of 0 to result. But H1 and H2 are both positive when we want to output a 1. You'll see in this row and this row, H1 and H2 are positive for outputs of 1, whereas in these rows, one of them is negative for the when we want the outputs to be 0. Now, this is really useful, a really useful intermediate result that we can make use of to eventually solve the XOR problem. But to use this info that we have in the table now, we need to actually now make use of activation functions. So let's apply the sigmoid activation function to the columns H1 and H2. You'll recall that when a negative number is input into the sigmoid function, the function outputs a 0, and when a positive number is input, the sigmoid function outputs a 1. So here are the results of applying the sigmoid activation function to H1 and H2. The results appear in purple here. If you take a look at those two columns that I've circled here, all you need to do is AND those two purple columns together and you'll get the desired output, which is the green column at the end of the table. You'll get the output of the XOR function, which is what we've been wanting our neural network to output throughout this video. As my note says here, the AND function can be approximated using a linear equation, which I show in this. It's the orange, purple, and white equation I show here. And when you apply this sort of approximate AND equation to the purple columns, you get the orange column results here. All we have to do now is apply the sigmoid function to the AND column to turn the negative numbers to zeros and the positive numbers into ones. And that's it. That's the result that we've been looking for. Nonlinear activation functions had to be applied to get the neural network to finally solve the XOR problem. Remember the AND function we performed on the purple columns on the previous slides? And how a linear equation can act approximately as an AND function. Well, the Y node in our neural network is that AND function. All three of the neural network nodes were initially just linear equations, and they took us really close to solving the XOR problem. But we had to use a non-linear activation function, the sigmoid function, to actually cross the finish line and get the neural network to actually solve the problem. The sigmoid activation functions were applied at nodes H1, H2, and Y, and they were the key to finally solving the problem. That's it. Thanks for watching.